that gives it a turning effect of the motion, right?
Yes, ma'am.
Are you there?
Yes, ma'am. Can you hear me, ma'am? Hello,
Yeah,
ma'am?
yeah, yeah. Yeah, now it's, yeah, hello, hello. Audible, audible. Don't worry.
Yes.
Audible you are. Okay. Uh,
Okay.
yeah. Yes. So basically, in that we had discussed the lever, beam, hinge, and all these things. Then second law, I had told you that the total torque applied over any given material will be equal to your MA. Done. Now, if we need to suppose further, if I am trying to resolve it in such a way that uh, let's just do the, what should I say? Let's find out a formula that how we will do for the torque MA. Okay. So it's a very small derivation over here, that in the last class, as I had given you, that the torque is equal to MA. Okay. Not MA, but exactly M alpha. Okay. And it has been derived as your mass into acceleration, that is tangential. Okay. All this is happening on an object which is kept at a distance from the rotational motion. Let's say r1 is the distance, and here in this direction, let's say the force has been applied. So acceleration will be applied in this direction. Understood, Akshita?
Yes.
Any doubts?
No, ma'am.
Okay. So here we are applying the Newton's second law and we get F equals to ma. But since the rod is been pivoted, okay, at the end, and the mass will move in a circle of radius r. Done. So the angular acceleration of this body will be given. Okay. And what will be the angular acceleration? So the angular acceleration is given by your normal acceleration over r. Okay. Acceleration basically are of two types, Akshita. One is tangential acceleration and one is, do you know about this term or shall I explain?
Yeah. Yes, ma'am. Tangential acceleration is when it's you said uh it goes like
Huh.
this.
Hmm. Yeah, go ahead. I'm listening.
Uh so basically, like, if this is the, I think if this is the Earth and this is the Moon, I
Hmm.
am, I had one example, ma'am. I just read somewhere, like, if that uh
Yeah.
this is the uh, tangential force, and then with this we measure something in the outer space, but I don't remember the exact thing, but something like this.
Perfectly fine. Perfectly fine. That is why I'm asking. Do you remember tangential acceleration is there? Okay. Let me write it for you. Tangential acceleration. And then after that, we are having centripetal acceleration. Okay. Now, centripetal acceleration provides the circular motion, whereas the tangential acceleration keeps it along the radius. Okay. Because when you define your centripetal force, no, in the last class also I had told you this thing, that the centripetal force, when you are defining the force which is applied towards the center and along the radius. So when you are saying towards the center, is basically centripetal acceleration. Okay.
Yes, ma'am.
Whereas when you are saying along the radius, it has been provided by tangential acceleration. Okay. So there are two factors. One is centripetal and one is tangential. Understood?
Yes, ma'am.
Okay. Hope I am making you understand.
Yes, ma'am.
Okay. So when you are saying tangential axle circle, when you are moving, suppose I am at this point. So I'll be having this tangent. Suppose I came at this point. So I'll be having this. Suppose now I came at this point. So my tangential will be like this. Hence I'll be performing a tangential acceleration from where I can the by the virtue of it I can say that every point my direction is continuously changing. Are you getting? So the
Yes, ma'am.
direction change is provided by the tangential acceleration, whereas the circular motion that I am performing is been provided by centripetal acceleration. Okay?
Yes, ma'am.
Okay, because you have to remain towards there. If I am at this point, I have to stay at this point at a radius r. If I am at this point, I have to stay here. I'm at this point, I have to stay here. If I am at this point, I have to stay here. Like this. Understood?
Yes, ma'am.
Okay, so when I am writing here, coming back to the point f equals to ma, so I have to remain in tangential acceleration while performing this motion. Okay, this is what I was trying to convey. Okay, and the rotation, sorry, the rotation is caused because the force provides a torque. Okay, the force
Yes,
provides
ma'am.
a torque, and that is also about the pivot. Where is the pivot? Here. Motion happen like this. Understood or not?
Yes, ma'am.
Okay. So the rotational force is caused because the force provides a torque, and it is about the pivot. Now, when you actually summarize this whole thing that I had told you, that F equals to m of tangential acceleration, where my alpha is given by A over R. Okay. Okay. So this alpha is the uh, angular acceleration, and this is tangential acceleration. All of them are different. Okay. Don't
Yes.
mix them, please. Basically, what I can write over here is that if I put this alpha over in this formula, I'll be having F equals to m alpha r. Right?
Yes, ma'am.
Correct or not?
Yes, ma'am.
Okay. Now let's multiply r on both sides.
Then it will
Done.
be F.
So when we multiply, yeah, exactly. It will become Fr equals to m alpha r square. So what is Fr? Torque. What will be
Yes.
this? M alpha r square. So I got a formula for torque now. Understood or not?
Yes, ma'am.
Okay, now when I am talking about a rigid body, it is made up of lot of particles. Okay, so when the torque is applied over a body, each particle experiences a circular motion. That means each particle experiences a small amount of torque. That is the turning effect of the force, or I should say, the torque is in the direction of rotation. Understood or not?
Yes, ma'am.
Akshita, wherever you are facing difficulty, please do let me know. Okay. Now consider the body, okay, which is given over here. It performs, let it have now two masses. Okay. That suppose we had discussed here with only one mass. Now let's discuss with two masses. Okay. Suppose this is my point, and from here, this is my M1 mass and this is my M2 mass. Okay. So
Yes.
let's say this is at distance R1 and let's say this is at distance R2. Done. And it is performing an acceleration over here. Any doubts?
No, ma'am.
Okay. So now here I am considering a body which is made up of basically two masses, and it is joined with a massless rod. Okay. Which is rotating about the end. Okay. It is rotating from here like this. Done.
Yes, ma'am.
Okay, with some angular acceleration a. So hence we can keep that my torque is nothing but m1 alpha r1 square for the first body, and torque 2, okay, is m2 alpha r2 square for the second body. So the total torque on whole body is given by torque equals to torque 1 plus torque 2. That
Yes,
will
ma'am.
be m1
Yes,
alpha r1 square plus m2 alpha r2 square. Done. But the
yes,
body is rigid. Okay. So both the masses will have same angular acceleration. Am I making sense?
yes, ma'am.
As the body is rigid, Akshita, so both the masses will have same angular acceleration alpha. So I can write torque equals to m1 r1 square plus m2 r2 square alpha. Done?
Yes, ma'am.
So torque will be equal to the sum of mr square multiply alpha. Understood? If I do the summation for all the particles, that is, I got this formula, no? Finally, from this I am predicting all this. So the summation of all the mr square, yeah, summation of all the mr square multiply alpha will be given as your torque formula for a relativity consisting of many particles. Any doubts?
No, ma'am.
Are you sure, Akshita? So
Yes, ma'am.
hence from here we define a new term which is known as moment of inertia, Akshita. So what is moment of inertia? Moment of inertia is defined as I equals to summation of all the particles are set. Done. This is known as moment of inertia. And its SI unit will be mass, so hence kg, and r square, hence meter square. Understood?
Yes, ma'am.
Any doubts?
No, ma'am.
So therefore, this formula is further simplified as torque equals to I alpha. Akshita,
Yes, ma'am.
please reply. Is it going correct with you?
Yes, ma'am. There's just little bit voice, uh, like
Glitch
you.
came.
Yeah.
Where did you not listen to anything? Tell me. I'll repeat that.
Uh, this the torch is equal to summation m alpha squared I am r squared times alpha. That one.
Okay.
Did you say
Okay.
something after that, ma'am? Like
Yeah.
you.
Yeah. I had said something. What I was telling is, as it is a rigid body, so the acceleration for all the particles will be same.
Oh,
Okay. Acceleration for all the particles inside the body will be same, no? As it is a rigid body.
yes, ma'am.
Yeah. So the alpha for this and alpha for this will become common in the equation.
Yes, ma'am.
So what will be remaining? M1 R1 plus M2 R2. So if I
Yes,
combine here what I had taken, Akshita, two masses M1 and M2. Let's say
yes,
for a rigid body, all the masses are behaving as small masses.
yes, ma'am.
Okay. So if
Yes.
all of them are behaving as a small mass, then what will happen?
Then
Or summation of M1 R1 will come to me. Understood?
yes, ma'am.
And if their masses and radius are of same thing, then it will be summation of mr square. Hence from here I got a new terminology named as moment of inertia. So what is moment of inertia? Mass into square of the radius from where it has been pivoted, okay, for a rigid body is known as moment of inertia. Understood?
Yes, ma'am.
Okay. So
Yes.
therefore torque can be further simplified as I alpha. Correct?
Yes. Yes, ma'am.
Now, moment of inertia is different for different shapes. Understood or not?
Yes, ma'am. Understood, ma'am.
Yeah. Moment of inertia is different for different shapes. Okay. Now I am giving you the formula of different shapes. Just note it down somewhere.
Okay, ma'am.
So the some common shapes I am saying. Suppose I am having a hollow cylinder. I am just discussing that is there in our syllabus. Okay. Suppose I
Okay.
have a hollow cylinder and let's say this is the radius. So the moment of inertia is mr square. Okay.
Yes, ma'am.
Second, suppose I have a solid sphere. Not solid sphere, let's say solid cylinder only first. Compare the things. Okay. If I have a solid cylinder like this, okay, so here it will be half mr square. Done. If
Yes, ma'am.
suppose I am having a sphere like this, so it will be having 2 by 3 mr square. What I'm writing? Yeah. 2 by 3 mr square. Square. Okay. So
Yes.
this one is for hollow. Now let me write for solid also in the same way. So for solid it will be 2 by 5 mr square. Okay.
Yes, ma'am.
Done. Now if I have been provided with a rod, okay, which is having a length of L. Okay, let's say the distance is L and it is having a mass M. Okay, so for it can be pivoted at two ends, from the center, from the end. Correct?
Yes, ma'am.
Okay, so if it is pivoted at end, then the formula will be 1 by 3 ml square. If it is pivoted at center, it will be 1 by 12 ml square. Done.
Yes.
Thank you so much. नहीं बस थैंक यू सो मच नहीं बस हाँ वीडियो बंद है हाँ वीडियो बंद है ओके Okay, coming back to the topic, Akshita, have you written all the things?
Yes, ma'am. Can you just scroll up a bit, ma'am? Just the diagram. Oh,
Yeah,
yeah.
sure.
And also the the fourth one, the yeah, yes. Yes, ma'am.
Are you done, Akshita?
Yes, ma'am.
Sure?
Yes, ma'am.
Okay. Now, on this, we are having lot of questions, Akshita, and it is coming in the exam. Okay. Let me warn, this particular topic is very important, and in all the time it comes in the exam, whatever I had discussed with you. That's why I had not discussed in the last class. I had discussed it today thoroughly, that what is inertia, what is torque, and everything. Understood?
Yes, ma'am.
So please do prepare this topic as it is coming in your exam. Done? Now after this, we are having rotational kinetic energy. Because obviously, when you are studying mr square, you must be studying half mv square also, right? So rotational kinetic energy is there. Suppose again it is pivoted and a mass m is here, which is kept at a distance, let's say r. So rotational kinetic energy, what you will say, that suppose if I should say a rigid body which is rotating, then each particle of the body is moving in a circle. So, although the body is not moving forward, each particle has its own kinetic energy. Okay. So, these kinetic energies of each particle will be known as rotational kinetic energy. Understood or not?
Yes, ma'am.
Any doubts?
No, ma'am.
Okay.
Can
So,
you give
for this
example for rotational kinetic energy, ma'am?
rotational kinetic energy, any object which is performing, suppose, rotational motion, let's say all the planets.
Okay, ma'am.
Okay, so they must be having its own energy, no, which is said to be conserved.
Yes, ma'am.
Okay, okay. So the kinetic energy is nothing but half mv square, and we are aware that v equals to omega r in the case of angular motion. Any doubt?
No, ma'am.
Hence, from this, applying this in the above equation, I can write my kinetic energy as half summation of mr square multiply omega square. Am I writing it correct?
Yes, ma'am.
Sure?
Yes, ma'am.
Okay, very good. So,
Once
half
again, I just write it.
mr square is your moment of inertia. So, it will be half I omega square. Done?
Yes, ma'am.
Akshita, any doubts?
No, ma'am.
So
Just
similarly, you can, yeah. Are
I
you
will
writing
just
something?
write. Yeah, yeah, yeah. 1 second, ma'am.
Okay,
Just give.
okay. Okay, sure, sure, sure. Take your time.
Yes, ma'am.
Are you done?
Yes, ma'am.
Okay. So the work done will be defined as F multiply delta S. Okay. And here my S is nothing but theta, linear to angular. Making sense,
Yes,
Akshita?
yes, ma'am.
Okay. And the connection between the two is theta equals to S over R,
Yes, ma'am.
or my S equals to theta times R. So this equation can be written as F theta R. Correct?
Yes, yes, ma'am.
Also we are aware Fr is the torque. Hence further it can be simplified as torque theta.
Yes,
Work
ma'am.
done formula. Akshita, anywhere got stuck? Please tell me.
No, ma'am.
Okay. Would you like to do one question?
Yes, ma'am.
Okay. Don't worry, I'm giving you a easy question. Just try to find out that if it is like doable or not.
Yes.
Okay, solve.
10 centimeter and mass kg and 10 revolutions. Solids.
Is it visible? Are you doing?
Yes, ma'am. I wrote down
Yeah.
all the quantities.
Okay. Done.
I got the inertia as 8 into 10 to the power minus 0, like 8 into 10 to the power -3.
Okay.
To calculate the uh,
Mm-hmm. Go ahead.
10 revolutions per second, 10 revolutions per second. Uh, can you do that now, like the second part? Like,
Okay,
uh,
okay. Wait. Yeah, we will do it. Question is, calculate the kinetic energy of solid sphere of radius 10 centimeter and mass is 2 kg, which is rotating at 10 revolution per second. So the RPM given is 10. Done.
yes, yes, ma'am.
So I guess that is the angular speed.
Yes, ma'am. Do we need to convert it or something? The
What?
Should we directly substitute it as 10, ma'am, for in the equation?
No, you do it as angular speed is nothing but 2 pi r.
Yes. Oh, yeah.
Yeah.
Yes, ma'am.
Yeah. So the radius is 10. So 2 pi multiply 10 will be 20 pi radians per second.
Yes, ma'am.
Now the moment of inertia, it is a solid sphere, right? Which is
Yes,
2
ma'am.
by 5 mr square.
Yes, ma'am. I found out the inner slide. I just need to multiply 20 with the answer.
Yeah, 2 by 5 multiply 2 multiply 0.1 square, right?
Yes, ma'am.
Yeah, because obviously it is given in centimeters, right?
Yes, ma'am.
Yep. Are you done, Akshita? Be quick.
Yes, ma'am. One second. Okay.
Yeah. So from there you will get the angular speed, right?
Yes,
So
ma'am.
kinetic energy is half I omega square. Apply it over there, isn't
Yes,
it?
I'm getting 0.789 something. Is that right? Or did I do did I?
0.79 you are saying, no?
Yes, ma'am.
See, first thing, moment of inertia should be 0.008 kg per meter square. Check. Is it correct?
Yes, ma'am. I just took it as 8 into 10 to the power minus 3.
Hmm. So half into
8 into
0.008. Yeah.
minus 3
Multiply to
20
20 pi whole square.
r square.
Yeah.
20 square. But why am
20,
I getting this, ma'am? One second.
20 pi whole square, no?
Yes, ma'am, I did whole square, but I'm getting 0.789. I
It
think
should come 16 joule.
one second, maybe I should one second. I think my settings
Yeah.
is 10 degrees. One second.
Hmm. Okay, I told you in the last class also it should be in radians.
Yes, ma'am. I used it for math. I didn't turn it back to radian.
Yeah, perfectly fine. Tomorrow, Akshita, may be holy celebration. So either I will take the class in early morning. So if you are available, or if not, maybe we will cancel the class. Maybe. Okay, Akshita. If I got the time, I'll take. Don't worry.
Okay, ma'am.
Yeah, because I'm at my hometown, no? So that's why.
Okay.
Hmm. You are not celebrating?
No, ma'am, I'm in South India, so I do want to celebrate, but it's not common like that much common here.
Oh, okay. Understood. No, in North India, it's very much common, no? So that's why.
Yes.
Hmm.
Is it okay if I send the image of what I, or one second, ma'am? Is it because of brackets?
You can share your screen.
Yeah. Now I got it, ma'am. I actually kind of didn't put the brackets. I did 20 pi hours. I did 20 pi squared. So that's why the was giving wrong value.
See, I'm writing
Yeah, ma'am.
because
I'm
it's nothing
15 point,
wrong.
15.7913
You
something.
got it right.
Yes, ma'am.
Yeah. So why to worry this much?
Okay, ma'am.
Yeah. You are going correct. Okay.
Yes, ma'am.
Because energy should be given in the whole number. So it should be like the number is 16 joules.
16.
Done.
Yes, ma'am.
Yeah. So let's move with the next topic, and that is rolling ball.
Yes.
A second. Showing some glitch in writing. Okay. Some issue is occurring. I don't know what. Writing. Is it visible to you?
Yes, ma'am. I can see the whiteboard.
Yeah. And I'm writing that part.
Yes, ma'am.
Good. So rolling ball. First thing is when a ball is received, when a ball is released on an inclined plane, the forces acting are as basically what happens here is suppose when you are rolling a ball, let's say here. Okay. And this is my ball. So the number of forces acting over this will be obviously your normal force, done, and
Yes, ma'am.
your G force, okay, your frictional force, all these forces are working in action. Understood or not? Okay.
Yes,
So
ma'am.
if the ball has a vertical displacement, let's say H, okay. If the ball has a vertical displacement, let's say H, then what are the energies, or I should say, uh, what are the particular gain of energies and loss of energies happening with this ball? So when it is rolling down, Akshita, it
Yes,
loses the gravitational potential energy and it gains the rotational and the translational kinetic energy, isn't it?
yes, ma'am.
Okay. So I will write it over here. When it rolls down, it loses gravitational potential energy and gains rotational and translational. Okay, do you understand with the both thing terminologies, what is rotational and what is translational?
Yes, ma'am.
Okay, so when it is doing like this, it is rotational,
Yes, ma'am.
and it is going like this in a straight line linear, it is translational. Okay, so it is performing both.
Yes, ma'am.
Making sense?
Yes, ma'am.
Okay, so it will be converted into this, and from this I can write it as that my mgh is equal to half mv square plus half I omega square. Understood or not?
Yes, ma'am.
Now, if the ball is slipping down the slope, then there will be no rotation, I guess. If it is slips, I'm saying, if it slips over the plane, there will be no rotation. Correct or not? It will
Yes, ma'am.
only show translatory. Hence, my mgh will only convert into half mv square. Making sense?
Yes,
So,
ma'am.
comparing both the equations, first equation and second equation, we can say that the rolling ball will travel down the uh, the inclined plane in such a way it will be slower when it is rolling and it will be faster when it is sliding. Making sense?
Can you repeat that line, ma'am?
Yeah,
The line.
sure. I'm saying when it is coming down from first and second equation, we can say that while it is rolling down, it will be little bit slower in comparison to the sliding one.
Yes, ma'am.
Okay. And if the ball rolls without slipping, then the point of the ball in contact with the surface of the slope has an instantaneous speed of 0.
Yes, ma'am.
I'm saying, suppose if the ball rolls without slipping, okay,
Yes, ma'am.
then the point of the ball in contact with the surface of the slope has an instantaneous speed of 0. Correct or not? Because the point itself is changing at every moment as it is circular in nature.
Yes, ma'am.
Making sense or not?
Yes, ma'am. Yes, ma'am.
Okay. And the point which is furthest from the slope has an instantaneous speed of 2v.
Yes, ma'am.
Why it is 2v? Because furthest from the ball will be the whole rotation. Whole rotation is having a diameter, a instantaneous diameter of 2r. Okay. So what will be the instantaneous speed? 2v.
Yes, ma'am.
Making sense? My
Yes, ma'am.
ball is here, Akshita. Here. The
Yes, ma'am.
furthest point will be here. So if it
Okay.
reaches here,
It
this
will go.
point reaches here, one it come here, then it come here. It will be double of the speed
Yes, ma'am.
because one time speed is v, double time speed is 2v.
Yes, ma'am.
Making sense or not? So the
Yes, ma'am.
angular speed of the ball and the translational speed of the ball are related by, obviously we are aware that omega equals to v over r, isn't it?
Yes. Yes, ma'am.
And I equals to 2 by 5 mr square.
Yes, ma'am.
Correct. So from this, I can deduce that my mgh is equal to half mv square plus there are many derivations. Okay, Akshita. If I am writing, please don't get confused. Half of I omega square. So what will be I omega square? 2 by 5 mr square v square, isn't it?
Yes, ma'am.
Over r square. Making sense?
Yes, ma'am.
Sure?
Yes, ma'am.
Okay. So therefore, this will become half mv square plus 2 by 10 mv square. When you solve all this thing, you will get this. M will get cancelled from all the equations and finally you will get v value as under root 10 gh over 7 for a rolling ball. Understood?
Yes, ma'am.
Okay. And these are the small topics. They may come in exam. So formula booklet is carrying the formula. It's just that you need to understand the thorough pointers of that. Okay.
Okay, ma'am.
Now angular momentum. Obviously, when we have linear momentum, we will be having angular momentum performed as L. So S is denoted as theta. V denoted as omega. Your acceleration is denoted as alpha, angular acceleration. Your force is denoted as torque. Correct or not?
Yes, ma'am.
Yeah. Then your linear momentum is denoted as angular momentum. Making sense?
Yes, ma'am.
Okay. And in that we call it as moment in linear, and here we call it as moment of inertia. Okay.
Yes, ma'am.
Any doubts?
No, ma'am.
Okay. So from here, angular momentum will be defined as F equals to ma or m into delta v over delta t. Okay. So F can be also written as mv over delta t. Correct? So
Yes, ma'am.
similarly, in rotational motion also, why n is not happening? Yeah. In rotational motion also, we can say that if my torque is equal to I alpha, this can be rewritten as I into del omega over del t. Just check the equations.
Yes, ma'am.
Making sense or not?
Yes, ma'am.
Okay. So my torque can be rewritten as delta I omega over delta t, which is nothing but angular momentum. Okay.
Yes, ma'am.
Any doubts?
No, ma'am.
Okay. So this is the formula. Okay. That if suppose I am aware that I equals to mr square, then my angular momentum, that is L, can be rewritten as mr square omega. Please write it in terms of t and omega, in terms of L, mr square.
Yes,
Any
ma'am.
doubts?
No, ma'am.
Okay. And if there is no external hindrance by the forces and the resistive air pressure, etc. things, then obviously, Akshita, you will see that the rotational motion is also conserved, and hence it works upon the conservation of angular momentum. Making sense or not?
Yes, ma'am.
Yeah, like conservation of motion is happening in the linear. So same way conservation of angular momentum will also happen over here. Understood?
Yes, ma'am. Yes, ma'am.
Akshita, any doubts?
No, ma'am.
Okay, now let's talk about our Galilean relativity. Okay. So what does
Yes.
the Galilean relativity and all these things predict? So let's start from the first pointer, and that is your reference frame. Okay.
Yes, ma'am.
Okay. So reference frame is nothing but the coordinate of x, y, z and t system, which denotes the space and time of a given object. Understood?
Yes, ma'am.
Okay. Because obviously when we are defining something, we define it with some relative position. Suppose where is my home? My home is nearby to my school. How much time do you take to go home? I take 2 kilometers to reach from school to home. So school here is the reference point. Without reference point, Akshita, you can never ever define what is your position. Think of it.
Yes, ma'am.
Okay. Now, depending upon this, we can also compare the motion of different things, like what is relative velocity. Not motion, let's say velocity. So, what is relative velocity? Relative velocity could be something like, suppose here a person is standing, here a car is going, and here a plane is coming towards it. Okay, my handwriting is thoroughly bad. I don't know how to draw it, but I hope you have understood. Okay,
Yes.
done. So basically, if this is my aeroplane, it is coming towards this with a speed of 100 meter per second. It is going with 20 meter per second and it is throwing a flash of light. Okay. So as per this person, the car is moving with 20 meter per second. Okay. And the plane is coming with minus 100 meter per second speed. Correct or not?
Yes, ma'am.
And if suppose now a person is sitting inside the car, then according to this person, the woman is traveling with minus 20 meter per second.
Yes, ma'am.
Plane is traveling towards him with 100 plus 20, that is 120 meter per second.
Yes, ma'am.
Correct or not?
Yes, ma'am.
Yeah. So this is the rest position. This is the moving position. So check how much difference is there when you consider the reference or frame differently. Understood or not?
Yes, ma'am.
Okay. So this was a small intro about it, Akshita. Let's continue the class in the next class. Okay. If you need
Oh,
the class tomorrow morning, please just do let me know as early as possible, nearly at 7, 8, 9. Whenever you wish, you can take. If you are having school, perfectly fine. We will
yes.
schedule it as per your regular timetable. Okay?
Yes, ma'am.
Okay, Akshita. So bye. Have a nice day.
Bye, ma'am. Thank you, ma'am.
Yeah, yeah. You understood everything, no, Akshita? Is there any issue?
No, ma'am.
Are you sure?
Yes, ma'am.
Okay. From my end,